welcome to the show. Make sure you've got your calculator with your logarithm button ready for you, okay? Today we're solving logarithmic equations. It's very fun. All right, write 27 to the 4x as a power of 3. Got a mustache hair in my mouth. All right, so 27 is 3 to the third power. And then remember, if you raise a power to a power, you multiply those exponents. So 3 times 4x would give us 12x. So it's 3 to the 12x power. Very fun. Evaluate log 4, log sub 4, log sub 5, 4. So you can't get a common base here. So you're going to have to do the change base formula. Remember, you put log 4 in the numerator, log of 5 in the denominator. Let's see what we get here. Oh boy, I don't know where the log button is on this one. I'm not used to this calculator. Well, maybe I'll just grab another one for now. This is perfect for this video. No, this is great. This is perfect. Oh my gosh. Oh my goodness. Yeah, maybe I should just start this vid over. Oh, there it is. Okay. Phew, that was close. So log 4 divided by log 5, 0.861. Great. Simplify 4 squared to the 2x minus 3. Okay, so they probably want us to multiply the exponents here. So 2 times 2x would be 4x. 2 times negative 3 would be negative 6. Great. Okay. What else we got? That wasn't even that bad. If 3 to the x equals 5, then log sub 3 to the 3x, well, I know that 3x is equal to 5, so I should be able to just substitute a 5 in there. So we could say log sub 3, 5. Basic substitution. If 10 to log 2x equals 10 to the third, then log 2x equals, well, look, both of them have a base of 10. So it says log of 2x, it's going to equal 3, right? Because they're already equal to each other. And that's going to be pretty convenient when we get to solving the equations. Hey, a couple of things. So remember, if you had something like this, we can kick that to the exponent to the front and then turn it into multiplication, right? That's going to be a pretty important thing when we're solving the logarithmic equations today. Also, if you have the same base with addition between them, you bring them together, you condense it, and you multiply. So this would be log 4, which then you can simplify. 4 to the first power equals 4, so you get 1. So you have to remember some of these old properties. Also, the big one is like if you had log of 7, and it has a base of 7. So if that becomes the exponent, oops. 17 or something like that. So if the base and the logarithm are the same, they just cancel each other out. Those are inverses, so you'd be left with just 17. So that's a property that gets used quite a bit today as well. All right, so my favorite way to solve these, if possible, because this is just kind of like a fun puzzle almost, is to get them to have the same base and then set up an equation. So 2 and 8 can both have a base of 2. So 8 is 2 to the third power. Once you get that same base, you can essentially ignore the base. These are equal to each other. So here we would be doing 3 times x, which is 3x. Here there's nothing to do with the exponent. So once you get the common base, just get rid of the bases. Solve what's left for the exponents. Our exponents have 3x equals x plus 6. And then you solve it like a normal multi-step equation. You subtract your x, 2x equals 6, and then you divide by 2, and you get x equals 3. Now you're going to want to double check these answers. If you want, you can put them into the original, or you can almost sneeze. There we go. So if we put them into the original, we'd have 8 to the third equals 2 to the x plus 6. So 3 plus 6 is 9. Now, if you want, you can rewrite 8 as 2 to the third. And then remember, you multiply the exponents. So it would be 2 to the 9th equals 2 to the 9th. Or you can evaluate it and get the actual numbers. 8 to the third is 512. 2 to the 9th, 512. So you should always check this. Now, some people will see 4 and 8 and they'll be like, oh, 4 goes into 8. But we got to get the common base with exponents. So we're going to rewrite 4 as 2 to the second power. And that's still going to the 3x power. And then 8 is 2 to the third power. And then we have the x plus 1. Again, we have the common bases, so you can almost ignore them at this point and just work on the exponents. So we're multiplying here. 2 times 3x is 6x. Over here, 3 times x is 3x. 3 times 1 gives you 3. You solve it, subtract your 3x from both sides, which gives us 3x equals 3. Divide by 3, and x equals 1. You're going to want to check it in the original equation. So 4 to the 3x, 3 times 1 is 3. Over here, 8. The 1 plus 1 is 2. So let's see, 4 to the third, 64. 8 squared is also 64. Yes! 3 and 27 can both have a base of 3. So we don't need to do anything to the first fraction, but 27 is 3 to the third power. We have the same base, so let's solve the exponents. 2x equals 3. Divide it by 2. You're left with x equals 3 over 2, or 1.5. Now if you were to substitute that into the original, 3 to the 2x, 3 over 2. So if you multiply 2 times 3 over 2, 2 times 3 is 6, divided by 2 is 3. So we end up with 3 to the third equals 27, and that's true. 3 to the third, 3 times 3 times 3 is 27. Now you're not always going to be able to get that common base. So remember, you can do whatever you want to both sides of an equation as long as you're keeping it balanced. If you do something to one side, you have to do it to the other side. So we can do that here because 2 and 7 don't have a common base, but we can log both sides. So we're going to say log of 2 to the x will equal the log of 7. Now remember, these technically have a base of 10, we just don't write it. And this is going to allow us to use that change of base formula, but there is a little curveball. We have this exponent, so we're going to kick that to the front and make it x times log of 2 equals log of 7. Now you also don't need to write the multiplication there, you can just write x log 2 if you want. I honestly prefer to write the multiplication, but we're going to get rid of that anyway here, because we're just solving for x. So we need to get rid of times log of 2. So we're going to divide by log of 2. So these cancel, and we're just left with x equals whatever this is. Now be careful, because some people will just want to they'll want to simplify there. Just put it in your calculator with the logarithms. Log of 7 divided by log of 2 is 2.807. 2.807. And remember, we typically just round those to the third decimal spot. So if we were to check that, 2 to the 2.807. Now we're going to get an answer that's close to 7, but it's not going to be exactly 7 because we rounded. So I got 6.998278119, and that's great. So that's close enough where we're like, okay, yeah, we rounded, so it's close. All right, let's try this one out. Again, again, we can't get a common base here because 5 with an exponent can't give you 200. So we can log both sides. Log 5 to the x minus 2 equals log 200. Then we're going to do that exponent property. We can bring the exponents to the front as multiplication. So it's going to be x minus 2 times log 5 equals log 200. And you're going to do this procedure so much that eventually you might be able to just kind of go to this next step where you're dividing by that log of 5. But let's not get carried away at this point. So these will cancel. We'll have x minus 2, which means we're still going to have one more step. So log of 200, so that's 20. Okay, log of 200 divided by log of 5 equals 3.292. And then, of course, we have to get rid of the minus 2 by adding 2 to both sides. So we will get 5.292. We should double check it. The original equation, 5.292. So let's see, 5.292 minus 2 is 3.292. So 5 to the 3.292 power gives us 199.99. That's pretty darn close to 200. Cool. 10 to the 2x minus 3 plus 4 equals 21. So first we're going to have to get rid of that 4. We want to kind of isolate the base with the exponent. So we'll subtract the 4 from both sides, which would give us 10 to the 2x minus 3 equals 17. And then we're going to log it. Whoops. I didn't even leave myself enough space there. Now, at this point, you might be like, well, is that kind of like where you have the same base and the number there, so it equals 1? Okay. All right, that's true. We can simplify that part, but honestly, it's just going to be easier if we bring our exponents to the front, like we've been doing. The 2x minus 3, kick it. And you have your log 10, which again, this is equal to 1, right? Because 10 to the first power equals 10. So sure, we could even do that now. Because 10 to the first power equals 10. So technically, this part is equal to 1. So then we could just say 2x minus 3 equals log 17. Or if we just keep going the way we've been doing these other ones, we can divide by log 10, which again is 1. So we're dividing by 1. So log 17 divided by log 10 is 1.230. So 2x minus 3 equals 1.230. So we'll add the 3. 2x equals 4.230. And then we'll have to divide by 2. 4 divided by 2 is 2. 2 divided by 2 is 1. And then 30 divided by 2 is 15. So x equals 2.115. If we did that in the original equation, we multiply by 2, which gets us to 4.230. We subtract the 3, which gets us 1.230. So let's see, 10 to the 1.23 power equals 16.98 plus 4, 20.98. We need to get to 21. We're gold. It's all just rounding stuff. But you should check it, make sure it works out pretty close. All right, if you look at the property here, if you have log sub b x equals log sub b y, then x equals y, right? Which makes sense because they're saying, look, these are both log sub 3. They would cancel each other out if we threw the official way to cancel it out is give them both a base of 3. So make it As long as you're giving it to both sides, you're all good. And then you could use that property where if it's 3 to the log sub third power, those would cancel out. Same thing would happen here. So you're left with 5x minus 1 equals x plus 7. And that's true. But if you remember the property, if you have the same log sub number equals log, that same thing on the other side, you could just solve for what's left. So we're just solving the 5x minus 1 equals x plus 7. So we'll subtract an x from both sides. 4x minus 1 equals 7. We'll add 1 to both sides. 4x equals 8. And then we'll divide that at 4, and we get x equals 2. It's always a good idea to check these. So if we sub that into the original, 5 times 2 is 10, minus 1 is 9. So this would be log 3, 9, log sub 3, 9. Over here, log sub 3, 2 plus 7 is 9. So log sub 3, 9 equals log sub 3, 9. And remember, 3 to the second power equals 9. So this would, in theory, simplify to 2 equals 2. We didn't even need to take it that far. We're just cool like that. All right, now here we go. You could solve this without just giving the base to both sides. If you think about when we were simplifying logarithms, we said, okay, going from logarithmic form to exponential form, you would say 3 to the second power equals x minus 5. Then honestly, this is the way I prefer to do it. And then you can just solve it. 3 to the second power is 9, x minus 5. And you add the 5, and you get 14 equals x. And if you were to sub that into the original equation, log sub 3, 14 minus 5 is 9. And this makes sense because 3 to the second power equals 9. So it works. The way the textbook will show you, which is great, is what we were kind of just doing on that last slide initially, where you're just going to give them both the base, whatever is in your little sub spot. So it was log sub 3. So we're going to give them both a base of 3, because these will all cancel out. So you're just left with x minus 5 equals 3 to the second power, which is 9. So it gets us essentially to the same step. To me, it's like, I don't know if I like just throwing a new base on stuff, but it all works. So here we have log sub 5, 3x plus 1 equals 2. Again, you could set up 5 to the second power equals 3x plus 1, the way the book would have you do it, and probably people smarter than me would tell you to do it, is give them both a base of 5, and then you can use your exponent property, 5 to the exponent log sub 5. These all cancel, so we're left with just the 3x plus 1 equals 5 to the second power is 25. I'm going to scoot down. Actually, I'm going to move over. We'll subtract the 1. 3x equals 24. We'll divide by 3, and x equals 8. You should substitute it back into the original problem. Log sub 5. 3 times 8 is 24, plus 1 is 25. And 5 to the second power equals 25. Fantastic. Oh, some old properties. Log 45x minus log 3 equals 1. Remember when we're condensing, when you have subtraction, that condenses as division. These have the same base. So we can bring them together as 45x over 3 equals 1. Now, I would divide that right now. 45x divided by 3 is 15x. And then we can set up an equation, 10 to the first power equals 15x, or you can give it the base of 10 on both sides. That will cancel out the logs of 10. So we would have the problem off the screen. We would have 15x equals 10 to the first power, which is just 10. And then we'll divide by the 15. And if we simplify this, we would get 2/3. Now if we substitute that into the original problem, log 45 to the 2/3, or times 2/3, minus log 3 equals 1. So 2/3 of 45 is 30. And if we condense it now as division, 30 divided by 3 is 10. And 10 to the first power equals 10. That one works. Can get a little scary sometimes. All right, log sub 4 of 100 minus log sub 4 x plus 1 equals 1. We have subtraction. I was scared I was running out of time. So we'll bring it together as division. 100 divided by x plus 1. So I'm going to bring in a new base of 4 to each side. So that'll cancel that out. So we have 100 over x plus 1 equals 4 to the first power is just 4. So we're going to multiply both sides by the x plus 1 to cancel that out. So we'll have 100 equals 4x plus 4. We'll subtract our 4, 96 equals 4x, and then we divide by our 4, which gives us 24 for x. If you substitute that into the original problem, we'd have log sub 4 100 minus log sub 4. 24 plus 1 is 25. Equals 1. Bring it together as division. 100 divided by 25 is 4. And 4 to the first power equals 4. Awesome. I think 2 more. Okay, here we go. We're going to have to check for some extraneous solutions here. So we're bringing it together as multiplication. So, oh my goodness. It would be log 5x times x minus 1 equals 2. Now, you can multiply that now or multiply it in a second here. We're going to give both of them the base of 10. So we can cancel out the log sub 10 right there. So we have 5x times x minus 1 equals 10 to the second power is 100. Now we're going to have to do some old factoring tricks. So we have 5x squared minus 5x equals 100. And when you factor, you've got to get it equal to 0. So we have to subtract 100. Greatest common factor is 5. Keep that out. X squared minus x minus 20, which would factor to x minus 5 and x plus 4. And our two answers there would give us positive 5 and negative 4. If we substitute those into the original problem, if we sub in 5, we have log 5 times 5 is 25, plus log 5 minus 1 is 4. So this would condense as log 100, and 10 to the second power equals 100. So that one works. Let's check the negative 4. 5 times negative 4 is negative 20, plus log negative 4 minus 1 is negative 5. So if we did bring these two together, it would come as log 100 equals 2. And then you're like, okay, 10 to the second power equals 100. But if you type in your calculator log of negative 20 it'll say domain error. You can't take logarithms of negative numbers. So anytime your answer comes out negative and you're going to end up with a log of a negative number, that's not going to be a solution. So this one becomes an extraneous solution. So you would just go with +5. Okay, but that's not necessarily going to mean anytime you get a negative number that it's not a solution, because if this was like log -4x and you were doing a negative times negative, which would then make it positive, that's fine. All right, so here again we have same base, so we're going to multiply them together. Logs of 12 x times x plus 1. All right, let's go ahead and multiply it. So it would be x squared plus 1x. We'll give them both a base of 12, which will cancel out this. So we have x squared plus x equals 12 to the first power is 12. We'll subtract that 12 onto the other side, which would give us x plus 4 and x minus 3. And then our two answers would be -4 and +3. Now, if you look at the original problem, they're both positive x's. So our -4 is going to be an extraneous solution, because if you had log 12 to the -4 right there, that is undefined. So you can't do that. So that means that one's out. Now, if we substitute in 3, we have log sub 12, 3 plus log sub 12, 3 plus 1, which is 4, equals 1. Bring them together as multiplication. And 12 to the first power equals 12. So only +3 works on that. Last one, let's talk earthquakes. The moment magnitude m of an earthquake that releases energy E in ergs can be modeled by this equation. On May 22nd, 1960, a powerful earthquake took place in Chile. It had a moment magnitude of 9.5. How much energy did this earthquake release? Okay, so 9.5 equals 0.291 e plus 117. Remember, the natural logarithm still goes with the same rules as our typical logarithms. So we're going to subtract 1.17 from each side. So let's do 9.5 minus 1.17, 8.33 equals 0.291 ln. And we're going to divide by that 0.291. And 123 divided by 0.291 is 0.625. All right. Bell will ring in 30 seconds. So I'll have to record part 2 of this in a second video. Hold on.